And share screen. Yes, share screen. Okay, so we are going to start with set theory, chapter 3. Okay, we say set theory, but actually we are not going to be doing set theory. Kind of lying here. What we are going to do is so-called naive set theory. Okay, so what does this mean? This means that actually we are not give exact definition of a set and of an element. Okay, I mean, this is something just like you learn in the primary school. Collection of elements. We are going to define the set like this. So, I mean, I say definition, but it is not a rigorous definition. Okay, the object, a set is a collection of objects. Okay. So this is actually, maybe I shouldn't write definition, but undefined. We leave it undefined. What is actually a set? This is not, because I mean, why this doesn't gives us a proper mathematical definition? There are some examples called paradoxes. I mean, if you define it like this, you can come up with paradoxes. For example, most famous one is the Russell paradox. So if your collection, the collection of objects are the all sets, okay, then is this collection a set or not? Is it inside itself or not inside itself, right? Collection of all sets you take, and then this set, is this set inside your element? Because if you are taking the collection of all sets, then that one is also should be a member of itself, right? If it is not a member of itself, I mean, if it is not in the collection of all sets, then it is not a set. But we define a set collection of objects, right? This is a paradox. Okay. Please mute all mics. Okay. So to learn, I mean, actual definition of the set theory, there is a course called Set Theory, Math 320. If you are interested, actually very interesting topics, and generally every term, not every term, every year, once in a year, you open that course. You can take that course in the future, maybe. Okay. Another thing is an element, which we are not going to give proper definition. Element or a member of the set. Is the objects in that set. As I said, these are, as the name suggests, naive terminal definitions, okay? So not actual definitions. So, I mean, if an object, let us say A is an element of a set, let's say capital A, then we write, this is the notation. A is in A element. If not, the notation is A is not element of A. Okay. So how can we represent sets? I mean, a set could be, we said that collection of objects. This could be anything. For example, set of colors or set of pens or set of people, right? Set of students, right? Collection of students. So it could be a set. Either we will define it like this by using words, or we are going to use some properties to define a set. Okay. So in primary school, I think you learn two things how to represent a set. One of them is the making the bracket notation and listing the all elements, right? Let us say A, B, C, D. So the set of first four letters of the alphabet, and you are listing it here like this, right? The set of first four letters. Okay, or what else? The set of 1, 2, 3, 4, 5, let's say. Right? You can list them. And there is, I mean, this way you can represent some of the sets. Or, for example, there are, in mathematics, we use, I mean, the foundation is actually constructed on sets. That is why sets are very important to do mathematics, because later on you will see that you will be working on with some objects or some definitions. I mean, you are going to define those objects. For example, in calculus, to be able to do the calculus, for example, to define limit, continuity, right? All of those things you are defining on a set. There's an underlying set there. What is that set? In the calculus on one variables, please mute microphones. In the calculus of one variables, there is real numbers, right? You are working on a set, real numbers. Without sets, we cannot do mathematics, okay? So that is very important for us. So during this course, we will see these number systems, mostly natural numbers, the set of natural numbers. In the book, it starts from 1, but we will include 0 there as well. So where does the natural numbers comes from? So there is a saying, who's saying, I forgot. It says that God-given. Natural numbers are God-given, the rest is human production. Okay, so actually except 0, we learned this like a counting numbers, right? 1, 2, 3, then natural numbers we add 0, but in some books they don't add 0. In some definitions they add to natural numbers. For us, we will put, and then integers, oh sorry, right, natural numbers. So the set of natural numbers and the set of integers. That's integers. Integer means whole in Latin. So whole number. So we add natural numbers. I mean, once you have the natural numbers, you can add the negative of that one, right? And you obtain integers. I mean, negative means in that case, actually we are not defining it like this, but we are defining an operation. And under this operation, we will say that every element has an inverse. So the operation is addition as an inverse. So when you add with this number, you will get the 0. So with respect to this operation, first you show that there's a 0, then the negative. So that is how integers are constructed from natural numbers once you have them. And then rational numbers. For the rational numbers actually we can give a definition like this. It is m over n, right? Such that these m and n are integers. This is how we construct rationals, right? M and n integers, and n is non-zero. Okay, rational numbers. Okay, then there is this real numbers. Okay, so the set of, let me write it like this. So actually in mathematics, God-given natural numbers are, it was a joke. In mathematics, we construct natural numbers axiomatically. So it has a successor and so on and so forth. We will do it at the end of the term. Peano axioms it is called. So these Peano axioms will give us the natural numbers. Then we will construct integers, and then we will construct rational numbers. But how we are going to construct real numbers? I mean, in the history, it is like this. You take a square of length 1, okay? And then you look at the main diagonal. And then you want to measure that distance, right? Assume that you are going to walk from somewhere to somewhere. You will measure that distance. So when they measure that distance, they see that it is not a rational number. It's square root 2, and probably you have seen the proof of square root 2. That cannot be a rational number, right? So there comes the, real numbers. That is the need of the real numbers. But this is, of course, not the definition of the real numbers. Again, to define real numbers, we have to use, we can define it in 2 ways. One of them is Cauchy sequence. We take all the Cauchy sequences on rational numbers and complete them as a metric space, which is, high-level mathematics. And also we can axiomatically define real numbers, just like natural numbers. There are also Dedekind cuts, things, constructions of real numbers. Anyway, we will, by the end of the term, I don't think we will show you Peano axioms. Please, mics. And I don't think we will do construction of real numbers, but in analysis courses, we should do. Maybe you can do it maybe in the second term or second year, first term. Anyway, but we will go back to these numbers when we are doing cardinality. Okay, so what else? In set theory, one important thing is, very important set, is a set with no elements, aka empty set. Okay, this is very important. And the empty set, it doesn't contain any element. Why do we need such a thing? I mean, it is important when we are doing, any kind of mathematics based on sets, but all kind of mathematics we are doing based on sets. So it is important to have empty set, and it somehow completes the set theory. And also you can think it like this: the empty set is the kind of the zero of the set theory. Okay, so in arithmetics, like in addition, like zero, identity element, and in set theory, empty set does this job. And the notation for empty set, this one. Okay, we will use that one for no elements. Okay, so for example, this statement, X is element of empty set, is always false, right? Because it doesn't have any element. Sometimes it's called null set as well, if you see in some writings. Okay, so what else? I mean, when you have finite many elements in your set, you can list them. But like in the natural numbers, integers or rational numbers, we cannot list all of them, right? So we should come up with a proper way of representing a set. And this is one of the most important definitions, I mean, in notions that we should learn. To represent a set, we should define its elements. How am I going to do this mathematically, right? And we will say that, for example, A is a set and X an element of A such that this, for the such that, it has this property. Let's say property Q. Okay. So this is how we are going to represent a set. You should learn how to read this set notation. Okay, so X in A and X has this property. For example, very simple one. Let's say N. It's an infinite set. Let's say, for example, X is an integer such that, and then such that X is even. Okay, or you can represent this more concretely. X is an integer such that there exists K, which is an integer, right? And, or such that you can say X is equal to 2K, right? So these are the definitions of these elements of this particular set, right? So it is the set of even integers. Or what else we can say? We can also write like this, consists of X. X is an integer and there existing K in Z. Such that n is equal to X is equal to 2K. Okay. Okay. So what else? You can give more and more examples of this type. Okay. And as we will continue, we will give examples of this one. And another important thing is the which we will be using in our examples a lot, intervals in the real numbers. Okay, so first one is an open interval. Actually in the book it says that bounded, unbounded. Okay, let us do this. Open bounded interval. So this is something like this. You take two numbers, okay, and this is the notation. This is not a couple notation, parentheses notation. X is a real number such that X is between A and B. Okay? This is also an infinite set, right? There are infinitely many elements. We cannot list them. Okay, then open unbounded interval, let's say. It could be two different things. For example, it can be like this. Can I? Maybe I should. It could be unbounded from the left, or it could be unbounded from the right, since there are only two directions on the real numbers. It could be this one, right? Real numbers such that less than A. Any real number less than A, or it could be A comma infinity. Okay, so both of them are an unbounded interval. Or what else? What else is this one? But this is nothing but all the real numbers. Okay, and then closed bounded interval. Closed bounded interval. We use square bracket notation. X in R real numbers such that X is between A and B. Okay. Of course, I forgot to write that when I say AB, A is less than or equal to B. Okay, always. We should assume that. Okay, what else? Closed unbounded. For that one, again, we have this minus infinity A. A infinity. So for that one, minus infinity. Oh, X. Okay, so these are for the closed bounded interval. And what else? We also have sometimes half intervals, half open intervals, or half closed, whichever interval. And A, B. X. Okay, so these are the intervals. Probably you already know them, but just to go over them one more time. Okay, now we will, by the way, this infinity is not a real number, okay? So it is just for notation for it is going to the infinity, okay? So it's not a real number. Okay. Now, what else is? Let us define some properties of sets, but for these properties, we have to define what is a subset, union, the operations then, okay? So let us start with the subset. definition subset. So we have two sets, and we call that the set A is a subset of B if, and the notation is like this, denoted by a subset of B if, let me write, since you learned the quantifiers, let me write quantifier notation. For every x in A implies x is in B, right? So for every element of A at the same time, element of B, then we will say that A is a subset of B. This is the notation for the subset, okay? And if this is not true, it is not the case. If it is not the case, what is the negation of this one? For every x, instead of for every x, if there exists an element in A which is not element of B, then A is not a subset of B, okay? It is not the case, then we write not a subset of B, okay? So just to get used to the notations. Now, I mean, this is being a subset, we will say that a set is always a subset. So sometimes if it is strictly contains, I mean, if there is an element in B which is not in A, if B strictly contains A, then we will write like this. So in this case, this means that there is some B in B such that B is not an element of it, okay? Okay, what else? We can give examples of subsets. So if it is not the case, I didn't write the negation here, maybe. There exists X in A and this X is not in A. Okay. What else? Remark. For any set A, the empty set is always subset. Okay, so for any set, and also a set is a subset of itself. So how am I going to show that? We will do lots of, we will ask you lots of questions like this, proving that a set is a subset of the some other set. What you are going to do is, the idea is, take an element, because the definition is for every x in A, x is also in B, right? So what are we going to do? Take any element from A, and somehow it depends on the defining properties of B. By using those, we will show that it's an element in B, in the case if it's a subset. If not, we should come up with an element A which is not in B, right? Okay, so let me try to give you an example. Let us say that A is this set. And B is this one. Okay, now the question is A a subset of B? Let me put one more. Okay, now this is not true, right? Because there is this element A in A, and this A is not in B, right? Because this element A and this element A are not the same, right? So this is a one element containing set, okay? A is just an object, but this one is a set with object A, okay? But this is just an object. So they are not the same, okay? So this is how you can show that it is not a subset of that one. I mean, when you have finite many elements, you can check one by one whether this every element in A is in B. But even if it is a finite but a huge number, this would be also hard to do it, okay? What else? Another property. You can write as a lemma maybe. So for every for all sets BC, if A is a subset of B and B is a subset of C, then A is a subset of C. Okay, so for example, how am I going to prove? Let me do as an example, very trivial one. So what do we have? If A is a direct proof, if A is a subset of B, then for every A in A is in B, right? And if B is in C, then for every A in B, A is in C, right? So for every A is in A is in B, and for every A is in B, that A is also in C, right? So we get for every A in A is in C. In other words, A is a subset of C. Okay, very simple, direct proof. Later on, you don't need to write even the definition for every A. I mean, we will be using if A is a subset of B, B is a subset of C, A is a subset of C, right? Okay, so another important thing of equality of sets. Two sets are equal to each other. Okay, so let A and B be sets. We say that the set A equals the set B, or equal to the set B, and denoted by A is equal to B, if every element of A is an element of B and every element of B is an element of A. In other words, if A is a subset of B and B is a subset of A. Okay, so this is important. We write it like this, not in the words, because once we are asked to show two sets are equal to each other, this is what we are going to do. Take elements from one of them, show that they are also elements of the other one, and vice versa. Okay, time passes quickly. Okay, what else? Equal, we did it. Okay, example. Let us do one example. Very easy one. X is this set. And B is this set. Okay. So if you want to show that A is equal to B, what are you going to do? Okay, here we should start with an element in, this is A inside B side. A, okay, then we have x squared minus 3x plus 2 is 0, which gives, if you like, x minus 1 times x minus 2 less than 0. So either x minus 1 is negative or x minus 2 is positive, or x minus 1 is negative, x minus 2 positive, right? So you are going to solve these two cases and you will see that then x should be between 1 and 2, meaning that so x is in B. So you showed this side. For the other side, you will take an element from B. Then what do we have? Then we have x is greater than 1 and x is lower than 2, right? So x is greater than 1 and x is lower than 2. So when we have these two things, then here x minus 1 is greater than 0, but x minus 2 is less than 0. Then if we multiply x minus 1 times x minus 2, one of them is positive, the other one is negative, so this is negative, which implies x is an element in A, right? Therefore, we are done. Let me write, therefore, A is equal to B. If you show both sides, A is inside B and B is inside A, then you are done. Okay, this is how we are going to show the A is equal to B thing. Okay, what else? We have time. Similarly, you can show, let us say, remark. If A is equal to B and B is equal to A, you can prove this actually. C, then A is equal to C, right? This is not very hard, straightforward. Another definition is the power set. This is an important one. The power, let A be a set. The power set of A, denoted by this curly P of A. What is it? It is the set contains sets which are subsets of A. So all subsets, the set consisting of all subsets of A, right? And this is a set and it is called power set. Okay, so for example, if your set is finite, you can write the elements of the power sets. Let us do for a small one. Even for a small one, it will be, let's say, A, B, C. What is the power set? First of all, it consists of all the subsets of A. So empty set is a subset of any set. Therefore, power set of A contains empty set. Then these are single element subset of A. Then any two AC. Then A itself, right? Any three A itself. So these are the elements of the power set of A. So one interesting thing is, what is the power set of the empty set? So it is a set consisting of all subsets of the empty set. So it is this one. So you see, notice that these are different things. This is the power set of empty set, and this is the empty set. These are different, not same. Okay, because this set has no elements, but power set has an element, which is the empty set. Okay, you have to be careful about this. What else? Okay, I think. Oh, if your set is in infinite set, for example, power set of natural numbers, so it's like lots of elements it contains. Actually, it contains uncountably many elements, but we will do later. Let's say a lot of elements. Okay. So by the way, the number of elements in a set is called the cardinality of the set. And we will do that topic a couple of weeks later. It's because it is, I mean, if you have finitely many elements in your set, whatever the number of elements, it is fine. But in the case of infinitely many elements, when you have infinitely many elements, then again they have cardinality, right? So there are different types of infinity. We will see that one later. For example, the infinitely many elements in the natural numbers and the infinitely many elements in the real numbers are not same. But surprisingly, infinitely many elements in the natural number and in the integers and in the rational numbers, they are same. Okay, we will come to that one, cardinality of a set, later, because we need you need to do functions first. Okay. What else? Oh, I come to set operations. Actually, maybe I should stop here. Otherwise, I will finish. How many things? I can finish this on Wednesday, actually. Okay, I will solve lots of questions then. Okay, I should stop here and do the set operations, because a couple of operations we are going to define next time on Wednesday. Union, intersection, difference, and universal set we will define. And then we will show some properties. And actually we will be doing practice. I mean, the aim of the this section, naive set theory, is not teaching you set theory. Just to emphasize because it is the foundation of mathematics, a foundational thing, but just to give you an idea how, you know, mathematicians build their work on the sets, and also to do practice whatever you learn in the logic section, the proof methods, right? So do the practice in this naive set theory, because the theorems or the statements you are going to asked to show would be really easy, and you can do many practice there. That's why we will define a couple of set operations, union, intersection. Actually, being a subset, we can also consider like an not operation, but so given two sets, you can obtain new sets by using intersection, difference, union. So that they are basically those ones, symmetric difference, so on and so forth, but you can define it from the difference. And also another operation is the Cartesian product, which is also a very useful operation. And we will just, do define those very easily and do lots of practice to show, to prove some statements. Then we are done with the, sorry, there is families of sets. Okay, one more week, and one more lecture. I need just 1 hour for the families of sets to define how we are going to represent them, so on and so forth. Okay, so let me stop it here.